Recording started. Okay, here we have Paolo going to talk about event hubs from Italy. And this is the first time that we do a remote session with live meeting, right? So bear with us. Right. Paolo, all yours. Go ahead.
Hi. Can you hear me?
Yes, we can hear you loud and clear.
Okay. So, hi all, and thanks for coming to this session for the Global Azure Bootcamp in California. In this session, we'll have a global overview on a new service in the Azure Service Bus family, the Event Hubs. We'll see how it provides great support and features for the Internet of Things solutions in the telemetry space and data ingestion. So, as Sam said, my name is Paolo Paterno, and I'll introduce myself in the next slide. So, let me introduce myself. Who am I? My name is Paolo, and I'm from Naples, in Italy. I am a senior software engineer in a company named Leonardo Ricerche that builds embedded products connected to the cloud and Internet of Things solution. So in my job, I constantly moving from devices to the cloud. I develop from low-level application and drivers to high-level application with the UI and cloud solution for the Internet of Things. I am Microsoft MVP on Windows Embedded and IoT, but focused on Internet of Things. So all related protocols and cloud platform about IoT. I am a member of some regional communities like .NET Campania and TinyCLR, that is an Italian community with a focus on .NET Micro Framework. Of course, I am board of director member of Embedded 101 community, thanks to Sam. To contact me for any questions, you have a lot of ways, socials and email. Every day I do my best to reply all, but you can be sure that I reply all. So, what we'll see during this session? The session is focused on the Event Hubs, one of the new services added inside the Azure Service Bus family, and it's related to one of the main communication patterns in the IoT, the telemetry. Telemetry is the first problem. Speaking about telemetry, we speak about a lot of data that a lot of devices, million, billion of devices, send to the cloud. For example, sensors, connected cars, smart homes, smart buildings, apps, and so on. We need to ingest all data and process or store them for extracting useful information and figure out what we can do with them. For example, analytics, machine learning, and so on. The first step could be to use queues and topics and subscriptions provided by Azure Service Bus. And we'll have a quick introduction on them in the next slide. The big problem is always telemetry, but at scale, when we have a million, billion of devices. And in this case, a very good solution is to use the new Event Hubs service inside Azure Service Bus, of course. We'll see why to use it, the related architecture and features, and differences with the queues and topics and subscriptions. Finally, I also have time to show you a quick demo about it. So let's start with the first problem, telemetry. Telemetry is one of the main IoT communication patterns. Every device sends data to another system, for example, in the cloud, for conveying information about the status of the device itself and the environment around it, using, for example, one or more sensors. temperature, pressure, humidity, light, and so on. The communication is unidirectional. The system in the cloud doesn't send any data or related information to the device. There are other IoT patterns for this, like notify, where the system sends data to the device, command, where the device receives a command request from a remote system, execute the command, and then reply to the system with a response, and inquiry, where the device sends a request to the system to have some information. Of course, the data frequency depends on the application and the conditions around the device. We can have devices that send data every few minutes or every few seconds. So, the first solution for telemetry and other patterns, other IoT patterns provided by Microsoft is based on queues, even if we can use queues for all the other IoT patterns, like I said. A queue provides a way to decouple a sender and a receiver so that the sender can send messages asynchronously and the receiver can get messages at its own pace. The messages are stored inside the queue. So we can have a sender who sends messages to the queue and a receiver who gets messages from the queue. Of course, we can have more senders, we call it fan-in, and more receivers, we call it fan-out. However, with queues, we apply the competing consumers pattern. Each message can be consumed by a single consumer and then deleted from the queue. More consumers fight on the same queue, but only one is able to get the first message available in the queue. The consumer can get the message in two ways. The first is a receive and delete, and the second is pick lock. With the receive and delete way, the consumer gets the message from the queue, and the system deletes the message. In this way, if the consumer crashes during message processing, the message is lost. With the pick lock, the consumer acquires a lock on a message and tries to process it. During the lock, the message is in the queue, but it isn't visible to the other consumers. At the end, the consumer can notify the system to delete the message because it is processed, or can notify the system to make visible the message to other consumers because it isn't able to process it. So the sender can call a complete on the message or an abandon on the message. You can think about a kind of cursor on the queue that provides the next message to the consumers. When a message is consumed, the cursor gives the next message to a reading consumer, to the next consumer. The other solution is based on topics. If you need to have more receivers who get same messages or filtered on some criteria, we can use topics and subscriptions. On the sender side, a topic acts like a queue. On the receiver side, each receiver has a subscription related to the topic. Each message inside the topic is replicated to all subscriptions for that topic. We can apply a filter on the subscriptions based on message properties so that we can differentiate the destination subscription. For example, we can have a receiver for logging interested to all error messages, and we can have a receiver for storing data interested to all info messages and so on. In this case, the topics provide the publish-subscribe pattern, different from competing consumer in queues. So what are the main features for queues and topics? The messages are stored but with a TTL, time to live. When it expires, the message is deleted and it's not available in the queue. Expired messages can go into a special queue, so-called dead letter queue. The same could be for so-called poisoned messages who are malformed that the receivers can process. We can have a special consumer on a dead letter queue that is able to understand why some messages are malformed and process them. A receiver can get a message from the queue and the service bus delete it, receive and delete mode, or the receiver can lock the next message, process it, and then confirms to the system to delete it. In the first case, as we can see, if the receiver crashes, the message is lost, already deleted. In the second case, if the receiver crashes, the message returns in the queue, and it's available for another receiver. We can have a request-reply pattern, as for HTTP protocol, with the request sent to a queue, and the response get from another queue. There is a way to correlate the request message ID with response message ID. The sender sets an ID on the request message and sets the name of the queue, the reply to queue, for receiving response messages. Advanced features are sessions for grouping messages and transaction to have send-receive feature completed in batch, like the transaction on databases. So, when the number of devices increase, we have the big problem, telemetry, but at scale. Hyperscale, million or billion of clients, and concurrently. We speak about 100 devices, 10,000 devices, 1 million devices, and all send data in parallel to the cloud. So we can see some examples about telemetry. The million or billions of devices we are talking about at scale could be devices in our smart homes or connected cars that sends data with different frequency, 10, 50 minutes or every minute. We can have also applications on PC, embedded system or smartphones and tablet that sends data. We can have games, and a great example is Halo that uses service bus as ingestion systems. So, here the ingestion and processing scenario. Starting from the left, we have different devices, different kind of devices. We have IP-capable devices that are able to connect directly to the ingestion system. They have enough resources like CPU and memory for a full TCP/IP stack and SSL TLS protocol support. Then we have low-power devices based on RTOS, real-time operating system. They aren't capable to connect to the cloud. They don't have TCP/IP stack support, but use other protocols stack. For example, BLE, Bluetooth Low Energy, ZigBee, Z-Wave, to connect to a field gateway, who connects to the cloud. The field gateway is like a bridge with full capabilities for cloud connection. For example, we can think about a Raspberry Pi or a Windows embedded compact-based device, and the future Windows 10 for IoT device. Then we can have legacy IoT devices that use custom proprietary protocol, but are able to connect to the ingestion system through a gateway in the cloud. This cloud gateway translates the custom proprietary protocol messages into related messages that the ingestion system can understand. We can think about IoT protocols like MQTT and CoAP. As we will see, the ingestion system, like Event Hubs, supports only two IoT protocols, like AMQP and HTTP. We can also have applications running on PC or smartphones that send data for monitoring or logging. So, after collecting messages, all data go into the ingestion system based on the Event Hubs. All ingested data are processed in different ways, from stream processing to long-term storage, and finally, extracted information are shown to the user with the right presentation layer. In this scenario, we can have web, desktop, or mobile application, or a powerful tool like Power BI. So now let's start with Event Hubs. Event Hubs is different from queues and topics because it provides the partitioned consumers pattern. So different from competing consumers in queues and publish subscribe in topics and subscriptions. Each producer sends data to a partition directly or with the partition key on the message. In second case, the system processes an hash from the partition key and obtains the related partition. Of course, same partition key is always related to the same partition. Each receiver consumes data from a partition, but more receivers are grouped inside the consumer groups. With consumer groups, we can simulate a publish-subscribes pattern. We can have different receivers who consume data from the same partition, but they are in different consumer groups. So, a consumer group is like a view on the data stream, and each consumer group can process data for different purposes, like logging, error processing, long-term storage, stream analysis, and so on. When receiver gets data from the Event Hub, the data itself isn't removed from the stream. This is the big difference from queues and topics. The cursor to get data from the stream isn't in the central system, like queues and topics, but it's on the receiver side. In this way, a receiver can rewind and reread all the data in the stream to process them in the same or different way. It's up to the receiver to save a checkpoint and remember what's the last data it read, to restart from there if it crashes. This checkpoint could be based on message offset inside the stream or related timestamp. The main Event Hub elaboration unit is called throughput unit, that we can consider like a virtual machine. Its role is to process data from one or more partitions inside one or more Event Hubs namespace. All the communication is based on the standard AMQP protocol or HTTP protocol, and the channel is encrypted using SSL TLS. Now we can dip into all the stuff inside the Event Hubs. So we can dip into all the parts that compose the Event Hubs. First of all, partitions. As I said, producers and receivers send and receive data to and from partitions in parallel. The default number of a partition is 16, minimum 8, and maximum 32. You can have up to 1024 after a request to the Azure support, and only in special condition. So, the event stream is partitioned for scale out. So, we have more partition for scaling out. Consumer and producer pull out and send event in parallels. So, in the next slide, we can dip into the publisher side or producer side. A producer can send data to partition in the following ways. First of all, it doesn't specify a partition. It can also don't specify a partition, and in this case the system uses a round-robin distribution. If we suppose an event hub with 8 partitions, it means that the first received message goes into partition 1, then partition 2, until partition 8. The next message will go into partition 1 in round-robin fashion. In this case, you can have a FIFO, first in, first out feature for events, because messages are spread across different partitions, and more receivers read them in parallel. The second way for the producer to send data to the partition is that it can specify the partition ID directly. So the producer can decide what is the partition he wants to send data. In the third way, it can set a partition key inside the message, and based on this partition key, the system processes an hash that is related to a specific partition. The system guarantees that for the same partition key, we have the same hash, so the same destination partition. So in the last two ways, you send messages to a specific partition directly with the partition ID or not with the partition key. So you can have FIFO feature for the messages sent by a specific device in that partition, if it sends data always to the same partition. Partition key is the most used because you can group data based on it. In the last choice, the producer can use a publisher policy. So on the system, there is a so-called publisher endpoint for each specific producer. A publisher is like a virtual endpoint in the cloud for a device. And related to this publisher, there is a policy based on a token, so that we can grant or remove access to the event hub with granularity on single device. Remember that the base access to the Azure Service Bus is providing using SAS, the Secure Access Signature mechanism. The supported protocols are HTTP, and it's useful if the device has a short-lived connection to the system, and it sends data with low frequency. It's better to use the AMQP protocol, Advanced Message Queue Protocol, for long-lived connection with the device that sends data with high frequency. In this case, there isn't the high cost of open and closing connection for every communication, like for HTTP, based on a request-response pattern. And another AMQP advantage is that SSL and TLS and shake is executed only one time on connection. The next part is consumer group. The receivers are grouped in consumer group, and we have only one receiver for partition. We can have more receivers on same partition, but across consumer group. We can consider consumer groups like views on the stream. So they provide publish, subscribe pattern like topics and subscription. At least we have one consumer group, the default consumer group, up to 20 named consumer group. Receiving message is a complex work on the event hubs to synchronize receiving on all partitions. To simplify the interaction with the event hub for receiving messages and handle fails, checkpoint, and so on, we have a specific Nugget package with the event processor that provides a .NET API abstraction layer for receivers. It provides the iEvent processor interface we can implement to handle more messages in batch. Each processor instance is a receiver for a specific partition, and it's registered inside a specified consumer group. All processors are managed by an event processor host. So, when a processor is registered for a partition, it has a lease that is used by the event processor host to handle failover and scale for us. It means that if a processor crashes, another processor acquires the lease and we are able to receive from that partition. If we start more processors for the same event hub, the event processor host handles a load balancing, assigning partitions across all available processors. So, for example, in the picture, we start with a single worker rule that uses an event processor host that provides 8 processors to get data from all 8 partitions. If we need to scale up, to scale out, we can create another worker rule, and the 2 event processor hosts will have both 4 processors to get data from 4 partitions in the event hubs. Last but not least feature is the checkpoint. We can use an API to invoke a checkpoint so that the processor saves its offset and timestamp in the stream inside the blob storage on Azure. It's used to recover offset information if the processor goes offline and then restarts. This package on event processor host saves a lot of developing time instead of creating manually receivers on partition and handle scaling and failover. So, the most important billing unit in the event hubs is the throughput unit. Throughput unit is the processing unit, like a virtual machine, for the event hub, and it's the main billing unit, even if we have to add the number of messages transmitted. Throughput unit provides 1 megabyte per second in ingress and 2 megabytes per second egress, with data retention of 84 gigabytes per day. One throughput unit can handle more partitions, but in this case, we have lower performance at lower cost, of course. For better performance, we need 1 throughput unit partition, but at high cost. Throughput units are used across more event hubs inside the same namespace. It means that a throughput unit can process more partitions across more event hubs inside the same namespace. So, in summary, what are the main difference between event hubs and queue and topics? First of all, we spoke about different patterns: competing consumers for queues, publish subscribes for topics, and partitioned consumers for event hub. It means that queues and topics are useful for telemetry, but also for command messages, when you need to send a command to a device from the system in the cloud. And they are also useful for inquiry pattern in the IoT space. For example, you can do it sending a message to a queue, and the device gets the command from it. In this scenario, the device can reply with command result on another queue, as I said. So we can implement request-reply pattern. The Event Hub allows unidirectional flow of data, so called event, only from device to the cloud. We can't have communication from the cloud to the device using the Event Hub. We can do it if we implement a receiver on the device for an Event Hub, of course. Speaking about the receiver side, with queues and topics, we have a cursor on the server. on the queue and on subscription, so that when the message is consumed, it is deleted and the cursor moves to the next available message. With Event Hubs, the cursor is on the client side, and the client needs to save a checkpoint to remember what is the offset or the timestamp in the event stream, so that it restarts from the last read event when it shutdowns or crashes and restarts. Regarding the messages retention, there is a TTL, a time to live on queues and topics. It could be defined at entity level, so I can define a TTL on a queue or on a topic on subscription, or on message level, and the message is deleted when TTL expires. On the Event Hubs, there isn't a TTL, but the messages are retained from 1 to a max of 7 days in the cloud inside the stream. The other difference are on security and authentication, but here queue topics and event hubs are similar. All the entities in the Azure Service Bus are accessed using SAS, Secure Access Signature. With a SAS policy, we can define the authorization on an entity, queue topic and event hub, for sending, receiving, or managing. When a device connects to the Azure Service Bus, it has to use the access key name and the related secure access password for the SAS policy. It is a valid both for queue topics and event hubs. Regarding the underlying protocol, we have a secure connection based on SSL and TLS. So the application protocol over the TCP/IP stack can be HTTPS or AMQPS. The number of SAS policies is limited up to 5 for namespace. It means that we have to use one SAS policies to group more than one devices for their authorization. So how can we solve this problem at scale with billion of devices? With Event Hubs, we have a more fine-grained policy. We have a publisher policy based on SAS token. Using only one SAS policy to access to the Azure Service Bus, a device can request a SAS token that will be valid for a limited period of time and only for the specific device with the specified name. This name corresponds to the virtual publisher we saw in the previous slides. So the device can use this token to send data to the Event Hub until the token expires or it is revoked from the central system. For example, we can block an hacked device that is trying to produce a data flooding. We can think about a denial of service attack from devices. Finally, Event Hubs doesn't have all the other features of queues and topics like the letter queue and transactions, because the main purpose for Event Hubs is the higher throughput, and all above features add complexity to the system and slow down its performance. So, until now, it's so beautiful. We saw a lot of features for Event Hubs. But what about the pricing? As I said, the main billing unit is the throughput unit that we pay per hour when it is active. So more throughput unit means more performance for processing partition at higher cost. Then we have to pay the events ingested and establish connection, as we can see in the tables. So we saw all the features about the Event Hubs. This is the demo I developed, and it's based on a scenario where we have a BLE devices and the IoT gateway. The demo consists of an IoT gateway based on a FatSpider board from GHI Electronics. We have a BLE module from an Italian company, Innovative, connected to this board, and we get data, temperature and humidity, from a Texas Instrument sensor tag. The data are transferred to the Event Hub using AMQP protocol, and they are shown on a dashboard developed for PC. Another interesting solution is to send data to the Connect the Dots dashboard that is web-based. Connect the Dots is a project developed by Microsoft Open Technology that shows how we can connect different boards like Arduino, Raspberry Pi, .NET Gadgeteer board-based to the cloud using Event Hubs and Azure Stream Analytics for processing them. You can find more information about this project in the last references slide. So, the demo is based on these main parts. Here you can see the picture with the FatSpider board with Ethernet connection and BLE module. In red, there is the Texas Instrument sensor tag that has a bunch of built-in sensors like temperature, humidity, accelerometer, and so on. On the right, we can see the monitor application with the two charts related to temperature and humidity value.
Hey, Paolo.
So, hi, Sam.
Hi. Let me interrupt here a little bit.
Yeah.
I want to put you on spot. How about after the event, you write a blog entry to share how you build this demo so everybody can learn from it?
Yeah. Of course. Yeah.
Okay. Thank you.
Okay. So, can you hear me, Sam?
Yes, I can hear you.
I hear a strange noise from the microphone. So, let me share my Visual Studio instance. Can you see Visual Studio?
Yes, it's coming through.
Okay. So, in this project, but I'll write a blog post on this, there is a one solution with a lot of projects. There is the AMQP .NET library that is a open source project from Microsoft that provides AMQP implementation for the protocol, for the AMQP protocol in C#. So we can use this library on all the kind of boards based in the .NET Micro framework or on .NET Compact framework, so for Windows Embedded Compact boards, or on PC for Windows 8 or also for Windows Phone 8 application. But I developed a library that I'll put online on Codeplex as open source project that I call Service Bus Lite. It's a wrapper on the AMQP library that expose the same API we have in the Azure SDK to interact with the service bus, so queues, topics, and event apps from the PC. The AMQP project provides some classes based on AMQP concepts like connection, session, and link. And I developed this library to simplify the use of AMQP protocol and connection to the event hubs, also on boards with the .NET Micro framework or .NET Compact framework. Then we have a Spider monitor. This is the monitor, the application that show the two charts we saw in the slide with the temperature and humidity value. I started because I already used this application, so we can see that on the charts we have already some values, because as we said, the data are in the stream from 1 day up to 7 days. So the application is starting and read the data from the stream. These data are already in the stream. Now I start my application on the Spider board. It will receive data using BLE module from the Texas Instruments sensor tag, temperature and humidity, and send this data to the event hubs. I can show you that the client receive data in this bag from the BLE and then create a event data message. The event data message is the class that is provided to send message, for sending message to the event hubs. We can send data and information inside the event data, setting properties. In this case, I set time properties and temperature value, and humidity for the other value. And we can also set the body of the message. We can set inside the event data the body serialized in JSON or XML format. But for few data, in some cases, it's useful to use only properties, as in this case. Then the client send the data. Let me check the code. Data, and then.
Hey, Paolo.
Hi, Sam.
Hi.
Any question?
Let me inject this here, because you have quite a bit of code here.
Yeah.
And a little bit difficult to follow through a live meeting. How about this? After the event, I would like to ask you to write a blog entry about what you're showing here. Right? And that way, everybody can follow this. From what I can see here, it seems like all the stuff that you use are shareable, right?
Okay.
Right. So how about the project source code? Is that something that you can share with everyone?
Yeah.
Okay, great. If that's the case, I think this would be a good blog post that you can write and share with everyone.
Okay, let me start the demo. So we can see the data in real time in the two charts, because these are data from the stream that are already in the stream. Now I connect the board to my PC and deploy this application. The board is starting. The assembly are deployed to the device. So the board now have an IP address and started to reading values. Now we will see the ANQP trace, the ANQP messages that will send to the event tabs. And in real time, the data are showed in the two charts of the monitor application. It's okay, Sam?
Yes, we can see it good. Yeah.
Okay.
Yeah, it's very interesting that you can show the real time here. I think everybody is very curious to see the code, how you do it.
Oh, yeah. I'll put it online as soon as possible after the event, don't worry.
Thank you.
Okay. So, I can stop the demo and return to share my slide deck. You can see the slide deck?
Yes.
Okay. We have only the last slide for references, where all the attendees can find a lot of information. I have to add my blog post, but I'll write it as soon as possible after the event.
Hey, Paolo, let me say a few things for you here, okay? So basically, what Paolo does is he takes the time to understand this complexity, and he works through it. Like, for example, for the MQTT protocol, he spent a lot of time understand that protocol, and then he put together the M2MQTT, which is a .NET library that support the desktop and compact as well as the micro framework. Basically, what he does is he spends the time to understand everything, and he make it, simplify it so that you can use that library without having to go through what he does to study it, right? And again, if you look at the project that he demoed, there's quite a bit of code there, and without some clear explanation, a lot of you're going to end up banging against the wall trying to understand everything, right? So one of the good things from here is we got Paolo to going to share with us how he does those code in his blog post. So keep an eye on it. Now, after the event, we will make these slides available. For the end of the day, I will give you the URL where we're going to post these slides. So don't worry about the URL. There are a lot of things to copy here, but you have access to that. And if you register to the event and we have your email on as part of the event, we will shoot out a post-event email to everybody with link to these resources. Okay, all right? And Paolo,
yeah,
you did a great job. Thank you very much. Very much. Right?
Thank you very much, Sam.
Right?
Thank you.
Hold on. Yeah, hold on here. Let me see if anyone in the audience have questions for you.
Okay.
So thanks for the great demo.
Okay, thanks.
So I'm curious, so your monitor application is reading the data directly from the Event Hub stream.
Yeah.
So if you wanted to save the event in the data stream, so your worker process, I think that's what it was, would that just take that data and write it to a table?
Yeah. You let me show just a few lines of code.
Okay.
So
Thank you.
So you can see how simple to use the event processor host. Okay. Can you see my code? Yes?
Yes.
Okay. Here we have the event hub processor. As you can see, we have to implement this interface, and we have a simple method, the process event async, where we receive all the messages in the stream, one by one. Here I enqueue these messages in another internal queue to show in charts, but here we can have also a connection to a DB, to table storage, to save the events. Understand?
Yes.
Yeah?
Okay.
Is it good for you?
Yes. Yeah, okay.
Okay.
And what sort of would you use a table like an Azure table storage?
Yeah. You can use any Azure services or local services. Any Azure services, table storage, blob storage, any kind of service in Azure.
Thank you.
Okay. You're welcome.
Another question for you, Paolo.
Yeah?
Hi, Paolo. Thank you very much for this presentation. I have just one question. How you get started with this stuff, using the connection between the hardware and the software? I'm totally new in this field, and I would like to have an idea how to get started. Thank you.
Oh, okay. I started to study IoT 3 years ago. And as Sam said, I started with the MQTT protocol and developed the end-to-end QTT library. Then I started to study the service bus for developing in my company IoT solution that could be able to decouple sender and receiver. And then I'll start to use the event hubs at scale for its great feature. It's not so difficult to start. You can find a lot of information online on Embedded 101 website, on my blog, and all the other people that have deep knowledge about IoT.
Thank you, Paolo.
Okay.
When we start late, so we're running late, so we're gonna close it up from here, so we can start the next session. Right?
Okay. Okay.
Again, thank you, Paolo.
Thank you, Sam.
Thank you.
Thank you, Sam. Bye. Thank you.